Right, so thanks for inviting me to this. So I'll just go through what I have. So I guess we're all interested in consciousness. And maybe it's better to start with a question which is similar to what Francesco already presented, but like, what is consciousness and how do you know what, if you have a system, whether it's conscious or not? So probably most of us agree with animals that are similar to ourselves, like these cats or dogs or babies or something, that they're conscious. But what if we go like more extreme and something like lizards or goldfish or even flies? And actually, because the talk is going to be focused on flies, I'm just curious as to how many of you would actually be happy to say that flies are conscious beings. Well, it's about half, so the other half is going to hate everything that comes next. But yeah, this sort of question that Francesco already brought up has like clear implications, like formations, with some disorder of consciousness, like vegetative state or minimally conscious or locked-in sort of syndrome. And we need to know, or we want to know, whether these people, these patients, or like animals or whatever, are experiencing something. So we have made, or the field has made some sort of progress in identifying potential markers of consciousness. And these are some example ones, like if you look at ERPs, evoked-related potentials, and spectral power or something from neural recordings, we can kind of, like in humans at least, kind of like distinguish patients from healthy conscious beings. But actually, if we look at it in the context of other things, like for example, measures for detecting COVID. So if you look at the performance in detecting consciousness for these measures, you can see like AAC like 0.75 or something like that. But if we look at something else like COVID, if you focus on the right column, you'll see that actually you're very good at detecting other things like when you're sick or something like that. So we're really bad at detecting whether something is conscious or not. And the question is why? Why can we do so well with detecting illness or something else? But when it comes to consciousness, we're not really that good. And probably it comes down to the way we discover markers. Historically, what people do is basically just look at some sort of data, some sort of recording, and then they look at it and go, oh wait, there's a difference here. So for example, in a awake person, if we measure EEG, we get this like very high frequency signal. But then when you're on anesthesia, we go, oh, hang on, it looks different. It's more low frequency. So if we characterize high frequency as low frequency, we might be able to detect consciousness. And that's how we sort of like go around discovering potential markers. But what about the things which we potentially aren't very good at seeing, something that's not visible to the human eye? Or another form of bias would be like if you're an expert in some particular analysis method, and then you go, okay, let's try this complexity measure or some other thing that I've been using to use in some other field, and like, let's just use this and see if it works. And we have this sort of bias in what we're already like good at. And the problem with these things is that there's probably lots of analysis methods which are just gone uninvestigated. So potential markers which just haven't been looked at before. So what I've been doing, or what I'm presenting today, is kind of like the complete opposite to what Matthew and Francesco have presented, which is very theory-based, from first principle things. This sort of approach that I'm going to be showing you is sort of like throw as many things at the wall as we can, and just see what sticks, what correlates with consciousness, basically. And from there, maybe we can, build some sort of theory, or maybe that inspires us with some sort of new insight. So this is possible using this toolbox called highly comparative time series analysis, or HCTSA. And basically this toolbox gives over 7,000 different univariate time series analysis methods. And these time series analysis methods come from like different fields, such like basic statistics, like measures of distribution, or like correlation, model fitting, from physics or economy or geology, just like everywhere, basically. And the idea is we want to apply these and see if we can blindly apply these to data, and whether any of these basically are able to detect consciousness or not. And the reason I want to apply is because probably the subject of consciousness is probably at the neural level. And if we do something like this in humans, you have to use like EEG or like you have to really invasive recording, which are very difficult to get in healthy people. Whereas in flies, you can sort of like stick an electrode right in the brain, and then everyone's happy and everyone's fine with it. And also, because we're doing this really exploratory type of stuff, we also want to use this registered report sort of format where like we really want to fix which features, what of these 7,000 features look to be prompting, and then do they generalize. So this is the registered stage 1 where we discover features, and then stage 2 we want to evaluate whether they generalize. So let's go to the data. So in stage 1 we have 13 discovery flies, and which are during wake and during anesthesia, and we just have a couple of reporting. And here are 2 reportings from a fly, and one of them is awake and one of them is under anesthesia, and I'm not sure if you can tell which one is which from looking at it. I certainly can't. So that's the sort of goal. Like, if you can't see any difference, well, what is the difference? And I'll just walk you through what actually happens. So we have these time series data, and what we can do from one time series is extract these 7,000 values, so corresponding to those 7,000 different analysis methods, each for each time series. And then if we just look at all the data, so each row here corresponds to one set of 7,000 values, and each one row corresponds to one fly, one epoch or whatever, and then each column corresponds to one analysis method. So here it is 7,000. And then if we just take, say, one row, and I'll just, one column, sorry, and then just flip, highlight it. Wait, I'm getting different. Yeah. So if I take this one column and just take it out, bring it here, and I just rotate it just for visualization purposes. What we can do with this is we have one set of wake values and one set of anesthetized values. And actually, I forgot to highlight, if we just look at this matrix again, the top half, these are reporting from, these are when the flies are awake, and the bottom half, these are when the flies are anesthetized. And you can probably already see a difference on the left and on the right. There are a cluster of features where the values for those analysis methods are greater during wakefulness and lower during anesthesia, and vice versa. And that's basically what we want to assess if it generalizes to other flies. So if we can do that by doing basically cross-validation with data where like we just take the values and train some sort of, we just have some distribution of values for each fly during wake and anesthesia. So red here is wake and blue is anesthesia. And we'll just do some very basic, univariate classification type thing. And then just do some sort of cross-validation where we like leave out one fly or something and then just evaluate how well this feature does when you do this cross-validation cross-validation procedure. And that's all stage 1. So at this point, we have performances of these 7,000 features, and some of them look promising, and some of them don't look promising because they can classify, they don't classify, or something like that. And then when we go to stage 2, we actually have a massive or much larger data set of 49 values flies, and the key thing is that these flies were not available during stage 1. We didn't see them, they were locked behind our collaborators who kept them, and we had no influence on how we did the analysis in the discovery flight because we just didn't know anything about these guys. So we have actually 49 evaluation flies from 3 separate experiments. So the recording procedure, the overall recording procedure is similar, but the goal of the experiment would have been different. So we have one data set where we have one concentration of anesthesia, and then another data set with different concentration of anesthesia, and then another one which is a wake and sleep data set, so no anesthesia, but the flies are either awake or not moving and considered sleeping. And then if we just look at all the values, so here I'm showing each row corresponds to the average recording for one fly from each of the data sets, and again, each column is one feature. Probably, I'm not sure what you guys think of this, but like I don't see any difference between the top half and the bottom half. And so probably the features are not generalizing. So if we just focus on like something like how significantly each feature is in classifying wake versus anesthesia, I'll show the whole thing. If you look on the left here, each line is if we consider just how many features are significant at each recording location, if we consider just one data set at a time versus 2 data sets at a time versus 3 data sets at a time. And as you see here, we just add more data sets, the number of features which are significantly generalizing just decreases. And in this case, when we consider all our data sets together, all the recording locations except for the most central recording location, there are no significant features which are able to consistently distinguish wake from anesthesia or sleep. At the most central panel, we have around 50 features, which you'll see on the right panel here. So on the x-axis of the right panel, you have the performance, the cross-validation performance in the stage 1 discovery flies. And this dot, the vertical dashed line is the threshold for significance for that data set. And you can see a lot of features do perform well in that one data set. And those color crosses there are representing markers of consciousness, which are pretty popular. So like SP summaries is spectral power related measures. And then we have like purple is sample entropy and green is another form of entropy and so on and so forth. And they seem to work in this one data set. But on the y-axis here, this is the average performance across all the data sets. And I've highlighted in black the ones which are significant, which perform significantly in all the data sets together. And you can actually see that none of the popular ones, like these spectral power ones, the orange ones, they don't generalize across all the data sets, which is kind of surprising. Yeah. So those with these features though, so what are they representing or what do they mean? So here it's just like the same matrix but it's rotated and I'm showing, so each row corresponds to one feature here. And I'm showing the features which are significant. And we actually get two clusters of features. The top one is blue cluster and this red cluster. And actually they're kind of similar, just split in sort of direction as to the effect of loss of consciousness. But we find features which are related to fractal dimensions. So I don't know if anyone here works with fractals or anything like that. I certainly haven't, so I don't know anything about them. But basically, if you just look at the time series and like sort of shrink the window and then zoom in and then expand the time series again, you see sort of the same sort of pattern. So if I just highlight this one, this is the best performing feature. The performance is on the right. This is doing this fractal dimension, and there are different versions of fractal dimensions, but this one is sort of doing this box counting method where like if you box the time series smaller boxes, you can sort of like count how many dollars, something like that. Which is kind of interesting because I don't know, maybe you guys know more about it, but I've not seen this sort of fractal thing in the consciousness literature before. So this sort of approach can sort of identify this sort of thing. And before I oversell it, this fractal thing could also be very something similar. We have to be very careful with interpreting these non-linear sort of features because they can correlate very well with like with more simple measures like autocorrelation, which is green features there. So take what I'm saying with a grain of salt. But what's the cause of this lack of generalization? So here I'm highlighting two features, or the distribution of values for two features. One which performed well and one which didn't perform well. So the top one is a spectral power related one, and the red markers are for wake observation, and the blue markers are for not awake. And the bottom one is for the fractal dimension related feature that I highlighted. And you can kind of see in both cases that the red dots are sort of, in general, like greater than the blue ones. But the difference is that if we look across the data sets, yeah, on the top here, these are highlighting the discovery slide and then the evaluation slide from each data set. You can see that actually the distribution of values varies across, or the range of values varies across the data set, such that even if the direction of the loss of consciousness for this particular analysis method is consistent across slide, if you just train a classifier, you can't really use that simply because the range of values is just completely different. So we can get around this, or like, to sort of address this, we also try this other thing, ignore this stuff, because we can also try this other sort of weaker form of generalization, which is not really classifying, but just looking at the direction of the effective loss of consciousness. And so that, yeah, these are highlighting potential reasons as to why the classifiers don't generalize. And maybe actually in a lot of cases we don't need to be so strong in our generalization. So like if you have a patient coming to the hospital, maybe they've been to the hospital before, so you have a baseline sort of reporting and you can compare to that. So this sort of consistency, which I'm going to do next, is sort of getting at that, where like you're concerned more about the direction rather than generalizing across the individuals. So what it looks like is basically, again, so if we just take a column and protect for visualizing purposes, instead of training a classifier at this point, what we can do is just take the difference. And then the idea is we consider the feature to be consistent, significantly consistent if the direction is, well, consistently above, one way or the other. And this is sort of the same sort of matrix which I showed before, but just showing the differences in values. So in this case, we no longer have on the top wake and a bottom anesthesia. This is just the top half, and then what's shown in the difference. And you can kind of see again in the discovery flies, there's like a clear cluster of features where wake is greater than anesthesia for those features, and vice versa for another cluster more to the right. And the evaluation flies, we also see something similar, unlike before with the raw values. So again, we have two clusters, one in one direction and the other one in the other direction. And then if we just look at how, if we look at the number of features which are significantly consistent as we consider more and more data sets, we do see some sort of pattern across channels. But more importantly, I guess, is that if we look at those popular markers like those spectral power related markers, if we look at the direction, they actually work. So what does this mean? What it basically means is we have to be careful when we're looking at any particular data set or any particular study, right? So probably if you have one experiment or maybe even two experiments which are similar, you'll probably be able to find some sort of analysis method or some sort of marker which is going to work in that data set. But you have to be very careful about making any sort of stronger statements as to it being related to consciousness, because what you need to do is you need to consider these like different sorts of anesthesia, different concentrations of anesthesia, different ways of losing consciousness, like going to sleep, or maybe even something like dreams. If we don't consider all these conditions together, probably the marker isn't going to work. And on top of that, there are also like recording differences, like the exact electrode replacement across subjects or something like that. So that's the take-home message of this sort of slide. And actually, if you look at the most consistent features, so the ones where like the across all the flies, the direction of loss of consciousness is most consistent. We actually don't find the popular markers to be the most consistent one, and actually find very simple measures of distribution. So these DM features are distribution of like kurtosis or skew sort of distributional measures, or like variance or standard deviation type sort of measures, which is kind of interesting that it's not even the popular markers which show up in this list. So just to summarize, I think there are problems with how we approach or how we have been discovering consciousness markers for these reasons which I already outlined. And when we sort of do this exploration thing and try to do this classification and generalization across multiple data sets, a lot of features, a lot of analysis methods simply don't generalize. And if we consider this weaker generalization, then we do see markers which are popular to be highlighted, but actually they're outperformed by these other very simple sort of variant sort of related analysis methods. And then the sort of next step is also everything that I showed here is univariate time series analysis, but of course you can imagine bivariate or multivariate, and there is actually a toolbox which exists called PySpy, which provides like 250 to 300 sort of these measures, including IIT. So that's, I guess, the next step to explore this. And with that, I'll thank you for your time and attention.
Thank you. Noah? So when you say the measure including IIT, which one?
Yeah, so there's definitely 5-star and 5G, and I think they also managed to implement IIT3. But there's a caveat that because the toolbox can focus on bivariate measures, it's just IIT for like 2 time series at a time, so you can't do the more complicated, like complex or like structured type stuff. Yeah.
I see. Thank you very much. Yes, maybe just follow up. Yeah. PCI or something.
cite this. Yeah. It's not really measuring phi exactly, but it's using its perturbational. Yeah, in T. So I think, you know, okay, is this better? Okay. So yeah, I'm just curious if you have thoughts about that. I mean, it seems like, you know, depending on your theoretical starting point, it's not necessary to have a perturbational approach when you are. It's just maybe possible in general to have a metric that generalizes perfectly like non-efficient. So just curious if you have thoughts about that.
Yeah, that's a very good point, actually. So everything that shown here, there's no sort of perturbations. So it's all observational, as you said. And actually, one thing which I forgot to put in the slide is one interpretation that I have is basically if nothing works, if we use this sort of method, then we really need a theory-driven sort of approach. That's, yeah, one take-home message, but I forgot to put that there. So I absolutely agree, and that's sort of the limitation of this sort of design and things that we're doing. But having said that, it's probably worth still just trying, basically, right? Like, we can try and make a theory, but I mean, probably the theory that you come up is going to be wrong just by, you know, you can imagine lots of different theories. So just by chance, it's probably going to be wrong. So why not just try, because we can, you do this sort of thing. Why not just try everything that we can already and just see what works? That's sort of this thing is trying to do.
Yeah, I think it's great work. So that's really
Thank you.
So that's, I agree with the approach. Of course, there's a big difference between maybe fly consciousness and human consciousness, and I was just wondering, how do you think this can be scaled? What's the future of these things? Do you think the results are applicable? Maybe you envision something with mice or mammals or something? Yeah, just comment on that, please.
Yeah, so the main like draw of using flies is basically flies only have like 10,000 or so neurons in the brain, and even though, so I'm not a neuroscientist, but that probably makes it a lot more easier or more feasible to interpret what these features are actually like, what's going on in the brain, which is causing these analysis methods to like get their measures, right? Whereas if you try to do something like in the rat or like human brain even, probably it's very unclear. So at the human level, you're probably going to get EEG or MEG or something like that, and the best you can do is like sort of source localization, but actually it's not really reflecting like the deeper activity or something like that. Whereas with fly, we can go all the way from the peripheral, from the eye to the center of the brain, and probably the recordings are more high quality in the sense that it's actually picking up the activity all throughout the brain. So that's the point. Yeah.
Oh, so great. Thank you for your talk and very appreciate your stuff. I'm asking more like practical questions. So I think for the experimental scientists, so we all tried a lot, internally. But once it has a more result, we don't publish it. So we don't really know what anyone else tried. And but then, for example, the recent AI and machine learning becomes so like collectively powerful because we have like benchmarks. We have a lot of models that's explicit and specific, like explicitly detailed how those models perform this data, and how they have different performance, and that drive the whole community forward. And I think this is a good starting point. And do you think you are or it's possible to build up that kind of community like machine learning? And I think that's maybe the only way to accumulate this kind of more result. Otherwise, we try a lot and we just come into our algorithm.
Yeah, that's absolutely right. And that's the reason why we want to take this registered report approach. So I'm not sure how common this registered report, if people are aware of it in the machine learning sort of community, but like basically you lock your hypothesis down and get a manuscript, a stage 1 manuscript in principle accepted. And what that means is, regardless of the results, it gets published. So if you find another result, it gets published. And what that does is it forces you to like be very explicit as to what you're expecting. And so in this stage one, basically the hypotheses are basically these features which we saw in our cross-validation procedure. These are the ones which we are looking for to generalize. And then of course they didn't. Yeah, I think that this sort of register report is probably very important to deal with this sort of lack of null result publication, because simply, you know, as we all know, like it's very difficult to like get those null results out, and no one really cares. I mean, not like in a pinpoint way, but like in a large sense, we care. Like individual paper wise, we don't want to see null results, right? So I think maybe this register report sort of approach, bringing that over or just making it more mainstream. That's probably a good way to go.